This is Cameron Chai from azonano.com, and I'm speaking to Joe Kernan from Witec Instruments, and he's going to show us their a300 system.
Okay, here you see a fully loaded a300 system. So it's a confocal Raman system right now running, but it's also an atomic force microscope and a scanning optical near-field microscope. So you can switch between these modes just by turning the turret. And here you see there's a holder for the cantilever. You see the cantilever attached to it. So just by turning the turret, you can switch to AFM mode. You can adjust the cantilever with this piezo-driven XYZ inertial drive XYZ stage, and can use the same sample, the same scanner, the same system for AFM and for Raman. For scanning near-field optical microscope, you just put into a different cantilever with a hole at the tip of the ensom cantilever, and then you scan with this hole over the sample and can focus light through that hole, detect it from below, or you can illuminate from below, detect from above, or you can also have we have also a reflection mode attached. So all these modes are available. So I want to explain you now our confocal Raman thing. So you see here the sample on this glass on a XYZ scanner. It's now scanning in a plane, a Y-plane. So the complete optic is fixed. We have a laser coming, I don't know where it is, coming with a single mode fiber. You went down here, collect the light again, block the laser line, focus it into a multi-mode fiber. This multi-mode fiber goes over here to an ultra-high throughput spectrometer with lens optics. So here the light is dispersed in the different colors, and we use here EM-CCD. So this is an electron multiplying CCD camera to collect all this spectra. So, and here below we have our control electronics, controlling the scan, controlling the synchronization, controlling also feedback for AFM and so on. And you see, since we have very short integration times, a single spectra, they look very noisy. But recently, or yes, actually here at PitCon 2009, we introduced a software extension, so you can now use the mouse and just move over these frequency axis of your spectra and see immediately here the corresponding image. So you can find, like when you tune for a television station, so we call it can call it Raman TV, you can find all the frequencies where there are some structures within your image. Yeah, so this is one extension, and today I gave a talk about it. The other one is what we call online cluster analysis. So you see here the blue line, this is the actual scan line, and so all spectra up to this line are combined to different clusters depending on their similarity. So here right now we have 3 clusters, and you see very clear the green one, which has here in the corresponding spectra this line here, and we have the red and the blue one. They don't really differ too much, because this is a two-phase system. So also we had added that, so a user can immediately see if there is some structure in it. He doesn't have to have any knowledge, because this whole cluster analysis thing is without any assumptions. Okay, by combining this Raman, where you get this chemical information, which chemical species are where, if you combine that with AFM, you have at least doubled your advantage. With the AFM you can get a very high resolution down to atomic steps or atomic features, but you have very low chemical sensitivity. On the other hand, with the Raman you have only optical resolution, so maybe 300 nanometers, but you have a very high chemical sensitivity. If you combine both on the same sample, then you can transfer the high resolution of the AFM to the chemical information of the Raman and vice versa. So then you can get let's say information out of your measurement with a higher resolution of the AFM and the chemical resolution, so you know exactly, okay, these bubbles there are PMMA, and this is polystyrene, and this is whatever, and this is silicon, and this is so you can really chemically distinguish what is what with the high resolution of the AFM. So if you combine it, it's comparable like the very old hand-colored black and white photographs, where you have a very high resolution black and white information from your photograph, and then you use just a very rough some colors to make them look like a colored photograph. And this color has a rather low resolution compared to the original image.
And Joe, who typically uses these sorts of instruments?
Oh, we have a very broad range of users. So many of them go, of course, to research facilities, universities, research labs, also research labs in industry. And it starts from life science, pharmaceutical things, semiconductor applications, coatings, polymer stuff, chemical stuff. Also in geology, we supplied one instrument for the Carnegie Institution in Washington, and they use it to investigate stardust. So from Comet Wild 2, they collected stardust, brought it back, and for heaven's sake, it was a safe landing of this satellite back to the Earth, and investigate these small, some micron in size dust particles. So that's a very broad, also beauty industry. So right now we have some skincare product under it, because that's a very good available sample, so oil and water emulsion. So it's a very broad range of applications you can cover. Also nano tubes, nanovirus, nano-optical devices, all this kind of stuff we can investigate.
Okay, and this is the Alpha 300. You've also got other products that you offer that are...
Yeah, we have also Alpha 500 and 700, and they have a motorized stage to position and to scan the sample with a stepper motor. So here you can go to scan areas up to 100 millimeters, something like this. And the Alpha 700 is designed to put on a 30 centimeter wafer under it, so you can position it. And this was a demand from semiconductor industry. So they have often problems with some defects or dust or contaminations on their wafers, and but because these contaminations could be in the nanometer range, they cannot identify chemically what it is, and if they don't know chemically what it is, they cannot tell where does it come from and how can we avoid that. So with our system, we can move precisely to these positions of these contaminations, do Raman spectroscopy in this area, and from the Raman spectroscopic data we can identify the chemical species which causes this contamination, and in most cases then it's clear from which process step these contamination come from, and how, of course, then how they could be avoided.
All right, Joe, thanks very much for that information.
Thank you for this interview.